So in this session, we're going to talk about providing QoS guarantees in an NVMe TCP software-defined system. Unfortunately, my colleague Alex couldn't make it to this conference, so I'll be standing in for him and mostly winging it, but I think we'll do fine. From DAS, which is to say direct attached storage, to a disaggregated solution like we see mostly in case of cloud vendors. What and why? On the left over there, you can see the traditional sort of data center infrastructure where we have compute nodes with their storage attached inside the servers themselves, which we've been doing as an industry for decades, but it has a number of challenges, mainly having to do with the flexibility and scalability. What do you do when you run out of storage in a particular box? What do you do when your storage needs of a particular application exceed what you can deliver, maybe in terms of performance? There's the issue of, say, failures and providing redundancy and so on. And then there's a matter of maintenance. How do you sort of upgrade these things and so on? And on the right, we can see a disaggregated solution that can serve the same needs much better. And I think earlier in the conference, we've heard Intel folks talk about rack scale architecture, and some of the other vendors talked about composable infrastructure that also provides this sort of disaggregation. And in this case, we can see a rack where most of the servers are the compute boxes, and then a number of servers provide the storage, in this case, Lightbits storage. But what we should note that unlike, say, rack scale architecture, using NVMe TCP, we're not limited to just whatever backplane fabric we might have in a rack, such as PCIe. This solution can span across the entire data center and certainly across multiple racks. So to provide you some context for the QoS discussion later on, first I'm going to give you a bit of a NVMe TCP overview. As a recap of fabrics, NVMe over fabrics as a whole, the initial implementations, prototypes for that were done around 2014, which is when the fabric standardization started. Around 2015, something called Fabrics Linux Driver Task Force was formed to work on the initial not initial, but to provide a prototype for the standardization effort as it matured. And at that time, it did all the heavy lifting of reorganizing the Linux NVMe stack to simplify subsequent adding of fabrics transports, and we'll get back to that later. In June 2016, of course, NVMe over Fabrics 1.0 was ratified, and in October of the same year, Fabric support was finally merged, both as a host and as a target, into Linux kernel 4.8. So why NVMe TCP? We already have a number of transports for NVMe over Fabrics, so why add TCP now? Well, the most basic answer is, of course, that TCP is a ubiquitous protocol. I mean, it's probably the most common transport we have out there. It runs on every box, from large refrigerator-sized solutions down to the tiniest IoT devices. It is a well-understood protocol. There's been research for decades going on around sort of solving the different networking problems around that. And of course, work has been going on implementations. Every operating system by now has a well-debugged and usually well-tuned TCP/IP stack. So that's a win-win right there. It's also pretty scalable in terms of threading. I mean, if you need more performance with TCP, you usually can just add a couple of threads and observe linear scaling in terms of throughput, and usually very minor, if any, increase in latency. Also, unlike some of the other NVMe over Fabrics transports that we have out there, it's well suited for large-scale deployments and longer distances, whereas some of the other transports require either dedicated networks that are typically very small scale, or some lossless fabrics that are very difficult to scale to larger data centers, certainly hundreds or thousands or tens of thousands of nodes. That's a very major challenge for the other transports, whereas TCP has been doing that forever. And it's an actively developed transport with major players continually working on it. As far as ratification status goes, the initial specification, TP8000, was ratified in November last year. It is an integral part of NVMe over Fabrics 1.1, which is on track to be published this month. On the right, you can see here the vendors who have been contributing either to the specification or to the implementations. So it's a multi-vendor thing going on with interoperability. In November 2018, at the University of New Hampshire Interoperability Lab, the first NVMe over Fabrics Plugfest included NVMe TCP testing at the POC level. And it's been a regular feature of these Plugfests ever since. As far as Linux support goes, the driver task force has been developing specifically NVMe TCP support for Linux since 2017. Initially, two different prototypes existed, one by Lightbits, the company I work for, the other by folks from SolarFlare. Eventually, these two converged into a single implementation that got merged later on into Linux. And this implementation, since it was developed side by side with the specification itself, it also provided input for the specification on what worked, what didn't, what issues there were, until in March 2019, NVMe TCP transport got merged into the Linux kernel 5.0, and it is already available in at least some of the major Linux distros out there, or will be available soon. But even before all of that happened, NVMe TCP as a transport has been running in production environments for a while now in the form of backported batch sets to earlier kernels. And you can head for our website to see links to some of these kernel drivers for the earlier kernels if you're looking for that kind of thing. So in a nutshell, NVMe TCP is a fairly straightforward implementation of a Fabrics. In this diagram on the right, you can see that at the logical level, we still have NVMe submission and completion queues going from the host to the controller, except in case of NVMe TCP, the actual NVMe request responses are being routed through the regular sockets API, and then through the TCP stack on each side. So the TCP is acting strictly as a transport layer for NVMe here, but it also contributes stuff like reliable transport and congestion control, which are also relevant to our discussion here. The association model in Linux, at least, is as follows. Linux typically has a single queue per core on the host side. There's one admin queue, and then the I/O queues are typically mapped one-to-one to cores. And the NVMe TCP transport provides an independent TCP connection for each of those queues. So there is no controller-wide sequencing or reassembly constraints or anything like that. All of these queues are operating independently. And we'll see how we can improve on this model a little bit later on in this talk. And I believe folks from Intel also talked this morning about how we can improve some other things with ADQ, and these things are orthogonal. The way that the NVMe commands are transmitted both ways is by encapsulating them in PDUs, or protocol data units, the structure of which you can see here on the right. These units include some checksums for which are called digest in this case, for the headers or the data optionally. And these get transported over TCP as a whole. There are several types of PDUs in NVMe TCP. There's, of course, connection, initialization, and termination, which are less interesting for this talk. Now, capsule commands and responses are the NVMe commands that are being sent from side to side, whereas the data, the unidirectional data PDUs are host to controller data and controller to host data, which can be used to transfer the data. And then there is a mechanism called R2T, or ready to transfer, which allows the target or the storage server to control the rate or to solicit data packets from the hosts or the initiators in the protocol. And this feature can be used to provide a form of QoS, assuming the target has some sort of logic to drive this mechanism in a sensible fashion. Here we have two diagrams of I/O flows. On the left, you can see the read flow, which is fairly pedestrian. The host sends a request, and then the target sends a number of data PDUs to answer that request. Whereas for write, the situation is a bit more interesting because there are actually two different forms of write requests. One is called in-capsule request, and that is when the host just bundles whatever data with the write request into the same PDU and just send this to a target, assuming the target supports this. This is an optional feature. It has certain performance benefits in some scenarios where there is no need for an extra round trip before the host can start sending data. And the second way of doing the writes is, of course, using R2T mechanism, in which the host first sends a request to the controller, which in case of a QoS implementation consults its internal logic to see how much data it is willing to accept from a particular host at this time, responds with that data to the host. The host sends that much data, and the situation repeats until the host is done with a particular write request. On this diagram, you can see the way that NVMe TCP fits into the general Linux NVMe host stack. So as I mentioned earlier, very early on there was an effort to refactor the whole NVMe host stack on Linux. And so by the time that NVMe TCP landed in Linux, it was a fairly trivial affair. It just plug and play into this stack, just as any other transfer protocol for RDMA. Most of the code that was generic was simply reused. And there were very few additions that had to be sort of custom hacked just to support NVMe TCP. And of course, in Linux, it uses regular TCP IP stack underneath, so there was no need to do anything in that respect either. Here we can see a number of Linux NVMe TCP host features, including stuff like zero copy, header and data digests, CPU affinity assignments. If you recall when I mentioned the queues and associations to TCP connections, so in Linux it's typically a single queue is pinned to a thread per core, and this is the feature that sort of allows that. There are a number of features that are still work in progress or just planned, and you can see them here down on the bottom, including stuff like TLS for transport security that is still sort of outstanding. And you can see these later in the slides. And with that, we can move on to how, given the transport that I just covered, how we can implement quality of service for that. In this case, in a Lightbits solution. So what is LightOS? LightOS is an NVMe TCP target that provides additional data services. So it's not a simple JBoF that just exports individual namespaces from individual SSDs to the clients. It is quite a bit more complex than that. And it was the first commercially available NVMe TCP open storage platform out there, which is not surprising because we also drove the specification itself. It is a software-defined solution. It can run on pretty much any standard x86 server with pretty much any commodity SSDs. We do provide sort of pre-certified solutions, but it can run on pretty much any hardware you can think of. And different customers choose very different configurations to match their needs. It's based on totally standard networking. There are no customer proprietary client-side hardware like NICs or whatnot, nor software like very custom drivers. It can just use any bog standard Linux NVMe TCP as a host or initiator. It is a high throughput solution with low latency, and importantly, with consistently low latency. It provides certain data services and, of course, QoS, which we are covering in this session. It can do streaming, compression, and decompression, as well as erasure coding at a wire speed. In this case, up to, say, 100 gigabits per second per node. It also does thin provisioning, of course. And in case a single node erasure coding is not sufficient, the solution also provides clustering for cross-node data protection that can, of course, recover single node failures. Now, down here at the bottom, you can see a sort of very general diagram of this solution. And on the left, we can see the front end, which is NVMe TCP target, really. It's a high performance, low latency target implementation. It's a proprietary custom implementation. It's not based on the Linux NVMe TCP target code. It's our own thing. In the middle, we can see what we call the global FTL, which is the bit providing the data services. And that's the backend of the system. And it's also a high performance, low latency solution to address some of the typical issues that a storage solution would face. And this bit manages all the SSDs that we can see here on the right as a theoretically single pool of storage, except, of course, you can configure it in various ways to suit the workload needs. And optionally, we can provide an offload hardware card to offload some of the data services that we provide. Though this thing being optional, customers can choose to go with doing all of that on the main CPU cores, and some do. It sort of depends on the workload in question and the kinds of services that they're interested in. It's a trade-off of where this work will need to be done, either on the main CPUs or on these add-on cards. And since this is a disaggregated storage solution, of course, it's going to face some multi-tenancy issues, right? Because now we have a number of clients, all, and by clients I mean different hosts, accessing a single storage server that will export different volumes to different tenants, to different services running on each of these hosts. And that typically results in somewhat unpredictable performance and even behavior for the services running on these client servers. Of course, the most obvious one is a noisy neighbor problem, where we have one of the servers that might be driving a lot of throughput, a lot of requests, high bandwidth, and so on. And there might be another client that is very latency sensitive. But because of this unfortunate interplay and them sharing a single storage server, the latency sensitive service would suffer, of course. There's also the matter of interplay of writes and reads. In a naive solution where we just export NVMe namespaces from the individual SSDs towards the clients, these SSDs need to do all this stuff that they usually do, including, say, garbage collection and wear leveling and whatnot. And while that SSD that might be under a lot of stress from writes is doing its thing and trying to garbage collect, the outstanding reads, of course, see their latency spike. And then you need to do stuff like pause and so on. And there's the matter of write imbalance across SSDs. If we just exported a namespace from a given SSD, again, to some very write-intensive server, and then a different namespace from a different SSD to a different client that is read mostly, we will end up in a situation where one of the SSDs is almost worn out, and now we need to replace it. Maybe individually, it might have contained some other namespaces of other tenants that were not, say, IO intensive, but now we're stuck with this situation where the box needs to individually be tended to and have its drives replaced one by one and so on. And it's also very difficult to provide any sort of performance guarantees to the different tenants, be that in terms of throughput or latency because pretty much all the stuff that I just mentioned, but funnily enough, the users of the storage do prefer to have some sort of SLAs or SLOs that they can take into account while designing their services to run on top of that. Of course, the naive approach to trying to solve all that would be to wildly over-provision. That is, to simply throw hardware at the problem, put in a lot more SSDs and NICs and so on, but that is clearly not a viable solution for most organizations because it's just very expensive. And so we can try and approach that using quality of service. In case of LightOS, there are 3 solutions that we're going to cover in this session. And over on the left, we have reads and writes separation. And this is something that happens both on the client side, on the host side, and on the target or LightOS server side. Then we have per tenant I/O capping, which is part of a LightOS server itself, partly on the front end, partly on the back end of the LightOS server. And then there is the issue of balancing the right IOs across the SSDs in the GFTL or the back end of the system. And we'll see how those 3 can help us achieve a somewhat better quality of service. So the first thing that we'll address is a read-write separation in the system. And this is kind of a classic networking, you might say, or queuing problem, which is a head-of-line or head-of-queue blocking. And in case of storage, this is most immediately obvious in case of reads latency being affected by writes and huge writes in particular. And down here, we see an example in this diagram of read requests, which are typically just a few bytes each, being queued or stuck behind potentially huge write requests, which are in red in this diagram. And the problem is, of course, that not only will these read requests not even leave the host towards the target before the writes clear the path, but they also will not be processed before the target can receive all of the data and start handling it. And the solution to that would be read-write separation, of course. So if you recall, I mentioned that in Linux, the association is typically TCP connection per queue, and the queues are queue per core. So instead of doing that, we can do something better. We can say, well, let's use 2 queues per core, one of which will be a read queue, and the other one will be a write queue. And the Linux kernel feature that allows this is separate queue maps that was merged in 5.0, I believe. So we can use that to provide this better mapping. And now we have dedicated queues for reads and writes. And on the target side, we can have a similar setup with dedicated queues in the NIC and in the system for read connections and write connections. And down below, we can see that the situation is somewhat better. I mean, for the huge writes, the situation may not have improved by much, but that's the laws of physics. We still need to transfer that data from the host to the target, but at least now the read requests, which are just these tiny metadata requests, can be immediately transmitted from the client or the host towards the target. And here we have some benchmarks of this feature being in operation. And the benchmarks are both for latency on the left and throughput on the right. And the setup was that we have a single writer on a host that does 256 kilobyte writes with a fairly substantial queue depth of 16. So it's keeping the pipes busy, so to speak. And we have 32 readers that are trying to issue synchronous 4K reads. And we can see that by enabling this fairly simple optimization, we can get an improvement both in latency and in throughput of a factor of 2, which is not bad for a fairly trivial change totally within the original specification. The second QoS mechanism that we are employing is I/O capping. And whereas the first mechanism could help us with requests initiated maybe by the same application or different applications on the same host, I/O capping can help us not only with different applications or tenants running on the same host initiating the request, but also across different hosts, which is our noisy neighbor problem here. And we can do that by doing I/O capping per tenant or per volume or per however we define this mechanism to act. And this also employs a multiple queues system on the LightOS server side. There's a subsystem called Arbiter that coordinates between all of these queues in the front end that receive the requests coming from the hosts. And then also between the parallel cores in the front end of the LightOS system that are handling all of these requests before any of this gets transferred to the global FTL or to the backend for actual handling in the storage. So the requests that are arriving from the clients are separated to different queues by a tuple of tenant for some definition of tenant. For instance, this could be a given volume on a system, which several hosts might be accessing at the same time, or it might literally be a tenant who happens to own a number of volumes or whatever. And then to take advantage of the previous QoS feature, also differentiated by whether these are reads or writes. And the I/O capping is done on a per queue basis, where the queues are being served by the system according to the quotas that they get from the arbiter, according to a certain configuration that the user can define when creating the volumes in the system or subsequently modify to map these to the different tenants. And of course, not all the volumes in the system will be experiencing the same high load at the same time. Some might be dormant for a while or might be descheduled from a specific LightOS server. So whatever spares that there are left in a given unit of time are simply distributed equally among the remaining queues, including best ever queues, that is to say, queues that had no I/O or volumes that had no I/O reserved for them. And this remaining bandwidth and throughput of the system is just being used to serve whatever connections that are active at a given period of time. And of course, requests to configure system in a highly oversubscribed fashion will not be respected. That would make sense. If you don't really want to provide any SLOs to your tenants, then you don't need to configure the system. Otherwise, that just wouldn't make sense. These are the benchmarks of I/O capping in action. And for this setup, we used a pair of tenants with 4 client servers each and a single LightOS server acting as a target. And the difference in how the tenants were configured is that tenant A has a reasonably light load with a queue depth of just 8, whereas tenant B is a very heavy bandwidth user with a high queue depth of 128. And each of them otherwise was exhibiting about the same workload. These were just random read requests, 4K requests, same servers on each side, and so on. And down here, this is a snapshot of Grafana charting the throughput of each of the 4 servers. As you can see, there are, on the annotations down below, there are actually 8 lines in there that are, their areas are shaded. And 4 lines belong to tenant A, of course, the 4 servers of tenant A, and the other 4 to the tenant B. And on the left side, we can see that when the I/O capping feature is enabled, both tenants got essentially the same bandwidth because this is how the system was configured. The I/O capping was set to the same limit for both tenants. And so even though they tried to submit requests at different rates, on the left side we see that we provided uniform service as per the original configuration of the system. And in the middle of the test, we went ahead and disabled the I/O capping feature. And we can see that immediately the tenant B clients that are a lot more aggressive in the way that they were submitting the IOs got the overwhelming majority of the bandwidth, effectively starving out the tenant A servers whose bandwidth dropped off to almost nothing. So that kind of demonstrates what sort of control you can achieve using some judicial arbitration on the server side. The third and final feature of this QoS solution that we have here is having to do with balancing the IOs across the SSDs and, of course, maintaining SSD endurance. Now, the general problem is that, again, in a naive system, kind of a JBOF that just exports namespaces from the individual SSDs directly to the hosts, the writes that will be landing on the SSDs will sort of be very uneven, shall we say, and will largely depend on the individual clients and what their workload characteristics were. And both write amplification and garbage collection activity will, of course, be different in order to accommodate for those write workloads of those clients. And the endurance of the SSDs will be correspondingly different. And, of course, the read latencies will depend on which SSDs the requests landed on. If the SSD was doing garbage collection, of course, the latency will be higher. If it experienced the heavy write workload at the time, the latency of the reads will be a lot higher. And to solve that problem, we just balance the IOs, as I mentioned. The IOs are being distributed evenly across all the SSDs. In a much as you would expect from an FTL, in an append-only fashion. There are no writes in place, no updates in place. It's a completely software-controlled process, including its own garbage collection. Now, this does not require any custom SSDs. This does not replace the FTL inside the SSDs. but it is something that can benefit from some of the newer initiatives, such as zoned namespaces in the NVMe workgroups that is currently under development, but it does not require any special hardware in order to do that. As a result, we get same endurance or nearly same endurance across all the SSDs, where the write amplification is balanced, wear out is balanced, read latencies are a lot more predictable, and we can actually start talking about SLOs for latency for different tenants and what the system can provide at very high consistency. That's roughly what I have for you today, guys. As I mentioned, LightOS was the first commercial high-performance NVMe TCP target with data services. And QoS was baked into the system as an integral part from the get-go in order to handle all of these disaggregated storage sort of challenges having to do with multi-tenancy and so on. And we are approaching the QoS in the system from 3 different angles, one being a read-write separation that provides improved and lower read latency by avoiding head of queue or head of line blocking, by providing per tenant I/O capping in the LightOS servers themselves that allow us to provide guaranteed and isolated performance to different tenant. And finally, by balancing the writes across all the SSDs in the system for improved endurance and more predictable both wear out and read latency. If you'd like to get more information on the system, you can find our website over there. And of course, if you have questions about the contents of this session, you can either ask me right now or contact Alex at that email address. So, any questions?
Do you have QoS for IOPS on your roadmap, other than by bandwidth or by capping?
We already have it. Yes. This is a slightly high-level presentation, but in actual reality, yes, this is one of the things that we can provide, yes.
Do your IOPS scale with load? Like if nobody else wants the bandwidth, is it still capped?
So as I mentioned, if once, so this is done once per quantum of time. So once all the allocations per that quantum of time were served, if there are any leftovers, we can just distribute them across whatever users there are, including the same one that was already capped. So no, there is no point in limiting something.
Well, sometimes there is.
Sometimes there is, but we just haven't seen very much demand for it so far, but it's obviously trivial to enable if there would be.
So it's not a hard cap?
No, no.
Just following up on this question, the latency depends on the load. So it's not like you have one budget and it guarantees the latency. So in terms of the capping, if the load gets higher, you can still accommodate more than the capped amount of IOS, but at the expense of higher latency for the others. So
Yes.
I'm kind of having a hard time figuring out how exactly do you decide when you can give the client something above its capping or when you need to strictly.
So these are slightly different questions. One of them having to do with if I have a single tenant and or maybe a couple of tenants and I cap one of them and there is no other traffic in the system, there is usually no good reason to keep capping it if we have spare capacity to serve. That's one thing. A somewhat separate thing is what sort of performance can the system reasonably provide without latency going sky high. And that's a different limit. So, well, don't do that. Don't go over the limit over which you can reasonably serve. So it's two different limits in the system.
But is there a specific limit in which you say, above this, I won't give anyone more than its capping, and below which I can give capped workloads to exceed their capping?
Yes, there is an upper limit beyond which, as you say, the latency would just skyrocket without actually improving the bandwidth. So there is no point to go beyond that.
I have a question about the global FTL. You're rearranging blocks all over the array. You must manage where these blocks go. How do you service devices in the array when the global FTL is scrambling?
When you say service, what do you mean by
Well,
that?
if I have 20 devices and one
Yes.
of them dies,
Yes.
it has blocks from who knows where.
Yep.
Right? Do you track them all and the file system?
No, we just write them at random and whatever. Who needs them? Write once, read never. No, of course we track all of them, and if a single device in a server dies, we do have an optional erasure coding across that, so the user wouldn't even notice that happened. You just yank the drive out, put a new one in, the rebuild happens in the background, and live happily ever after.
How do you manage the quality of service across the data center? Typically, my customer would not want to manage it node by node. He needs a holistic view of things.
Well, that kind of depends on what you mean. Well, our customers are the guys running the data centers, but their customers, their internal customers, are actually people running the services. So when one of them asks for a volume or creates volume, it is very important to manage the sort of SLO that they can provide for that particular volume, and it is a single volume thing that will be served from typically a single box. That's a well-defined thing. But beyond that, of course, in a clustered environments, there is a cluster management software that takes care of deciding what should land where, what the capabilities of the individual nodes in the cluster are at any given point in time, maybe to move the data accordingly or whatnot. So that's done, of course, by the cluster management software. It's not part of the data plan per se, right?
And the cluster management software is something that you develop?
Of course, yes. This is part of the solution. This is not exactly an open source thing. This is a product that we provide. It is a software-defined storage product, so you can get a bunch of RPMs, but this is a product that comes with its own management system, REST APIs and whatnot, monitoring and so on.
Because like in a virtualized world, a VM which has a data store that is backed by this LightOS server could move around, could go somewhere else. So the orchestration needs to be integrated with the virtualization world.
Sort of. Some systems already provide some infrastructure systems, like, for instance, Kubernetes, already provide ways of virtualizing that kind of thing, such as storage with, for instance, persistent volumes. So we do have a plugin, CSI plugin for Kubernetes that allows you to sort of let Kubernetes handle that. And we also have other integrations in progress, so that's kind of offloaded to the system that manages the rest of the infrastructure.
I should visit your website.
Please do.
So in the IO capping lab result that you discussed,
Yep.
you had two separate tenants, but both of them had pretty much the same code that you had, right?
Come again, both tenants what?
You had the same quota being allocated to both the tenants in that particular example.
Yes, in this particular configuration.
My question is, what are the different parameters on which you could decide what quota should be that is assigned to each tenant? I'm assuming if there are different queue depths, that might be a way to determine which tenant gets how much quota. Is that a way? And are there other parameters that
The queue depths are not much of a consideration in terms of QoS configuration. I mentioned the queue depth because that's just how the workload generator was configured. So as a sort of an indication of a load that was sent towards the target. On the target side, the QoS is not configured in terms of queue depth at all. There are different knobs you can turn in terms of requests and throughput and so on. Okay, thank you guys.